Okay, so now let's move on to the main portion of our lab. In task 1, we're going to be studying half-wave control rectifiers using SCRs and the UJT triggering circuit that we already saw, and observe the corresponding wave shapes. So, and as I said, we're going to be using Proteus, right? So this is the circuit that we're going to be constructing in Proteus. So let's open up Proteus. This is the window that you get, right? We can create a new project. So we go File, New Project. Select a name for your project. So let's say 2 task 1. Select where you want to save that. So select your output folder. Then click next. Okay, so we want to create a schematic. So we're going to be working with schematic. So we select create a schematic from the selected template. And we can just use a default schematic. We're not going to use a PCB layout, so we can click we do not create a PCB layout, and we don't want firmware project, so we can just select no firmware project and click next. So we want a schematic. This is where we'll be saving our project, and then we can click finish, and this is the window that you will get. Again, this should be known to you. I'm just going through it very quickly. So I'm assuming that you know how Proteus works. Now, so the circuit that we're going to create is this, and what we have is we have our V sign. Okay, so this is our input voltage. This is our UJT triggering circuit that we have already seen, right? This is our SCR or thyristor, and this is the output or where output that will observe our rectified voltage across. Okay, so we need a sinusoidal source, we need resistors, we need a variable resistor, we need a capacitor, we need a UJT, and we need a thyristor. So let's select all those components. So go to the library. So if you press P, it will bring up the library. Let's get our sinusoidal source first. So V sine. Okay, so if you write V sine in the keywords, it will bring up V sine. Double click on that, and it will add it to your it will add it to your screen. Okay. We need a resistor, so that is called RES. If you add RES, it will select this RES device, which is a generic resistor. Double click that, add it. We need a variable source. So the variable source is called a potentiometer, right? So you write POT, and then you write -HG. So we're going to be using this high granularity interactive potentiometer, and that is called POT-HG. So double click that, add it to your window, and we need a capacitor, so CAP, and that will give you the capacitor. So that's a generic non-electrolytic capacitor, right? So that's the type, and double click that, and we need our UJT, so just write UJT, and we're going to just use a generic UJT, right? We're going to need an SCR. So again, we're going to be using the generic SCR, right? And I think that's about it. So now let's build the circuit as we see in our lab sheet. So first we have our sinusoidal source. We have a resistance across that initially. We have our variable resistance here. We have our capacitance. Then we have our UJT here. We have resistance at the top and at the bottom of the UJT. The UJT connects to the gate terminal of the SCR. So place the SCR here. And we have resistance at the bottom of the SCR. Okay, so let's rotate these. So this one should be rotated. Right click, rotate anti-clockwise, and then line it up. Similarly, this should be rotated. The SCR is fine. This should also be rotated. So select that, rotate anti-clockwise. Okay. Next, let's complete the circuit. So this is connected to this resistor. I think we can lower this a bit. Okay, so this resistor is connected to R2 here. This terminal is connected between the potentiometer and the capacitor, right? This is the emitter terminal of our UJT. So just connect the diagram as in your lab sheet. Okay, so in Proteus, what you do is you go to the terminal and you'll see a pencil come up, click, and then it'll start drawing the wire, and then go to the point where you want to connect it to, and then click again. It will complete the wire. You should know this, so that's why I'm not explaining. So and our UJT, sorry, our SCR will be connected to this terminal here. So I think that is our completed circuit. Now let's input the values. So this is 330. These are both 1K. This is 220. So this is 330. These are both 1K. This is 220. This is, I think, 0.1 microfarads. And the potentiometer has a maximum value of 120 kilo ohms, right? And with the potentiometer, you can see that it says 50%. So you can change what it is, right? So if you click on this arrow right here, it will increase, so we can see the value increasing. So that is basically the percentage of the maximum voltage. So if you keep it at 50%, right, it will be 60 kilo ohms. So that's how this works. The source, we can set it to, I think, 20 volts. 20 volts amplitude, frequency of 50 hertz. And that is basic. We also need a ground. So the ground, you go to terminals mode on the left here, select ground, place that in your circuit, and then connect it. Okay, make sure you connect it. So this is our completed circuit. Okay, now we're going to be observing the output across this resistor, right? So we need a potential. We need an oscilloscope. So at the left hand side, go to this button here, which says below the probe mode, so you can have an instrument support button, right? So this is the instruments section, and you can see at the top we have an oscilloscope. So put that in your circuit. And the thing you have to remember with the oscilloscope is whichever point you connect it to, so say I connect it to this point, it will show you the output voltage across that point with respect to the ground. Okay, so you don't need to connect the ground to the oscilloscope, but whatever point you connect it to, it will show you the output with respect to ground. So at the A terminal, so these are the 4 terminals, the A terminal, I'm going to observe my voltage across output voltage of the SCR, which should be a half-wave rectified output. And let's say at the B terminal, I want to see my input voltage, right? So I'll connect it to the input terminal. So then I can see the input voltage as well as the output voltage, and it will show me both with respect to the ground. Okay, so that's what you have to keep in mind. Once your circuit is completed, you can click run at the bottom here, and that will start running. Okay, so see, we have our outputs. Now, one thing you should keep in mind is that if you accidentally close this, right, and if you stop, and once you run it again, you might not see the oscilloscope window. To bring that up again, what you have to do is you have to go to debug at the top here, select that, and then you can see at the bottom we have digital oscilloscope. So click on that and it will bring up the oscilloscope window again. Okay, now for the oscilloscope, we have basically we're working with channel A and channel B. So the yellow one is channel A, that's the output from the SCR. The blue one is channel B, that's the input voltage. And C and D are the pink and green ones. We don't need this, so we can just turn this off here. So you can see at the channel C portion, we can switch it to off. And same for channel D. Okay, let's bring this on the same scale. So with this position marker, you can control the position of the channel 1. So let's place it at 20. Okay, so I want to place both at the same position. So channel 1 and channel 2. Okay, so these are the scales. Okay, so this is the scale of channel 1. This is the scale of channel 2. If we make it a 2 millivolt scale, we can make it a 5 millivolt scale, we can make it a 10 millivolt scale. Okay, so let's keep it at 5. And so the position, this is the horizontal position, right? So if we drag this, we can change that. And this is our time. So now we're working with a time interval of 1 millisecond. We can change that to 2 milliseconds to see 2 waves. We can change that to 0.5 millisecond, right? So that's our time interval. So let's keep it at 2 milliseconds so we can see the 2 wave shapes. So, and if you click one shot here, it will pause, right? So it will pause instead of, so auto will make it continuous. So you can see that it's continuous, it's continuing to increase. And if you click one shot, it will just pause at a specific time. So let's say this time. So as you can see, during our positive half cycle, right, our SCR starts conducting at this point, and then we have a volt output across our resistance. Okay, and it goes on for most of the positive half cycle, and then during the negative half cycle it does not conduct. Okay, and then again at the positive half cycle it starts conducting again. So that is basically our half wave rectifier output. I hope you understood that. One thing we can do is let's vary the potential across the RV1. Okay, let's decrease it a bit. Let's go to 30% and see what that does. Okay, so let's run it now. Debug digital oscilloscope. So now we have to change, I think, the time scales. So just click on this button called auto here, right, and it will start generating our curve. So I think the triggering is it happens a bit faster now, so you can check that. So vary the values of your RV1 and see if that changes when the SCR triggers. But basically what we are seeing is we're getting our half wave rectifier, controlled rectifier, where we trigger the SCR at a certain point. Okay, so this is task 1 of your lab. Now for task 2, we're going to be observing a full wave control rectifier using the same, mostly same circuit. Okay, so to make it full wave rectifier, to make it a full wave rectifier, first of all, we're going to input a bridge from the feed between the source and the port circuit that we have already constructed in task 1, right? So what the bridge will do is it will convert the bidirectional voltage to a unidirectional voltage, right? So, and then our SCR can conduct for both half cycles. So we're just inserting the bridge to make sure that our input is unidirectional. So we have pulses, we have only positive half cycle pulses. Okay, so that's the only difference between our task 1 and task 2 is that we're inserting a bridge between our remainder of the circuit and our sinusoidal source. Okay, so it's very simple. Let me just go through it quickly. So go to your circuit. You can just disconnect this portions, right? So just disconnect the source from everything else. Bring that here and go to your library. So press B, write bridge, and select the generic bridge rectifier, right? Click OK, and then you can place that in your circuit. Okay, so how you have to connect that is connect the positive and negative terminals like this. So like so, and then you connect this portion to the bottom of our previous circuit and this portion to the top. Okay, so all we're doing is we're inserting a bridge between our original circuit and our source. Okay, so my original circuit is the same as it was. I am using the UJT for the triggering of the SCR. The only difference is I'm inserting a bridge so that our input voltage is now one dimensional rather than two directional, bidirectional. So our SCR can conduct for both positive and negative half cycles. Okay, so we're sort of using a loophole to make a full wave rectifier, but in this case we can see how our SCR triggers for both the positive and negative half cycles. Okay, so again, terminal A of the oscilloscope will observe the output across, or the output of our rectifier, and let's put terminal B at our output of our bridge. So that's the positive after we have converted, or we have rectified the initial voltage source, and let's put C to our original voltage source so we can see the difference. Okay, so let's run the circuit, go to debug and select digital oscilloscope, and let's turn on channel C. So channel C was initially off, so let's turn that on. Okay, oops, I've made a mistake. So let's connect that to the positive terminal instead of the negative one. So let's connect this to the positive terminal of our sinusoidal source. Right, now let's run it. Click debug, go to digital oscilloscope, and so this is the output that we're getting. So let's bring this all on the same scale. So channel B is the rectified voltage, right? Channel C is the original voltage, and channel A is giving our full wave rectified output. Okay, so you can observe that, and so this is basically our full wave rectifier using our SCR. So observe this, and then in your lab sheet you'll see a portion where you have to draw the output, right? So just take a screenshot of that output and then insert it with your lab report. So that was task 2, where we build a full wave control rectifier using our SCR and our UJT. Okay, and lastly we're going to look at a full wave rectifier using triac and diac. So with this one, I'm not going to show you the circuit, how to build the circuit. You can build this by yourself, and I'm just going to show you the type of output that you should expect. So construct that on your own, and then after you simulate it, you're going to give an output or attach your output with your lab report. So once you construct it, it should look something like this. Okay, and then if you run it, okay, so let's run it, and we can go to our oscilloscope, turn on auto, and then pause it at a specific time, and you can see that this is the output of the triac, so the rectified output, right? And this is our input, the red one is our input. Okay, so if I turn the red one off, you can see that this is the sort of output that you should be getting across your triac. So construct this by yourself and then attach it with your lab report. So that's your lab task. So your lab task is recreating task 2 and then attaching the output. So take a screenshot of the output and then attach it, and also constructing task 3, then attaching a screenshot of the output. Okay, so that is the end of lab 2, and I'll see you all in the review class. So please go through the video before you come to the review class, and you'll have your lab report due 2 weeks after you complete your review class. So thank you everyone, and see you